Welcome back to Physics 141 Online. In Chapter 3, we've been studying two- and three-dimensional motion. And all of the essential physics has already been covered. What really remains is to get lots of practice applying the physics equations, in particular for projectile motion, which is the kind of two-dimensional motion that we have near the Earth's surface, applying that kind of knowledge to solving problems. And it just takes a certain amount of time and repetition to do this well. So what I want to do is show you the solution to a really simple example problem that illustrates a lot of different principles for how to go about solving these problems. A ball is thrown from the Earth with an initial speed v0 at an angle of theta above the horizontal. And the two parts of the question are first to find the maximum height the ball reaches, and then secondly to find the speed of the ball when it is at its maximum height. And the problem tells us that the answer should be and can be in terms of v0, theta, and g only. Now of course there might be numerical values. There might be a 2 or a 4 or a 6 in the answer. That's okay. But what I mean is that the answer should only include, the answer that you get for the maximum height the ball reaches should only include v0, theta, and g. It can't, for example, include time, or it can't include some other quantity that we don't know. So v0 and theta are givens in this problem. And because of that, even though they're not given as numbers, but the symbols are given, so that means they can appear in the answer. Now, first of all, let's draw a sketch. Okay, the identify step in this problem is to realize what kind of problem it is. And so we've got a problem, since it's clear that this object moves near the Earth's surface, we've got a problem in projectile motion. And that's two-dimensional motion in free fall near the Earth's surface. So we will use the 2D motion equations. Simple enough. All right. Now, in order to develop a solution and a plan for the solution, we need a sketch. So what's the sketch look like? Well, here I will draw a vertical and a horizontal axis system that I'll label, of course, as y and x. And we will assume that the ball starts off at the ground, at the Earth level, at the origin here. And it's shot up at some, you know what, I don't really like that track that I just drew. It's a little too high for the space that I have available. So I'm going to draw it at a little more shallow angle. So there is the vector that indicates its initial velocity, its initial direction. And v0 is the speed, which is, of course, the magnitude of the velocity. Now, as it begins to rise, then, of course, now it's under the influence of the Earth's gravity, and we know that its trajectory will look like a parabola, like this. And we're interested, of course, in the maximum height. And what we know about that maximum height will be important. But the quantity that we're trying to find is indeed this maximum height. And since I know that the y direction is my measurement of height, then I'm going to call this delta y. And that's the quantity we're trying to find. Now, in order to decide which physics equations, which of the 2D motions equations I can use, I'm going to go through the trouble to write down what's given in this problem, and then that will usually give us a clue to what kind of equation we should use. So what's given in this, I've also forgot to label the angle theta. And when it says that the ball is thrown at an angle theta above the horizontal, right, it means that you would start with the horizontal in the positive x direction and rotate upwards an angle theta, and that would give you the initial trajectory, like this. So what we are given, and some of this is really simple, it's a projectile motion problem, so we know that a sub y is equal to, a sub y is equal to negative g, a sub x is equal to 0. No acceleration in the x direction, because there's no force acting in the x direction. What else do we know? We know v0, which is the speed. Now, what's important about that is that if we look at the motion equations don't have v0 in them. They have v0x or vx0, and they have vy0. So those are the things that we want to find. And so they're not given directly, but it's pretty easy. If I just draw a little vector diagram here, there's my v0 vector, and I know that it's got x and y components. And those are what we call vx0 and vy0. And the angle theta, again, is in that triangle. And just a little bit of trigonometry with the realization that that's a right triangle shows me that I can write vx0 as equal to v0 times the cosine of the angle theta, and vy0 similarly is v0 times the sine of theta. So vx0 and vy0, those are the components of the initial velocity vector. v0 is its magnitude, or its speed. Now, if these equations don't come naturally to you when you look at that sketch, for example, just remember your trig functions, right? The cosine of theta is the opposite over the the adjacent side over the hypotenuse. So it's vx0 over the hypotenuse, which is v0. And with that ratio, if I simply multiply both sides by v0, I'm solving for vx0, and it gives me the equation here. vx0 is v0 cosine theta. So if it's easier for you to start with the trig function and then use that to solve for the component, that's fine. But once you do this problem, this kind of a problem several times, you will quickly be able to just write down these initial components. Now, be aware that sometimes these components can be negative. And no one's necessarily going to tell you that. You have to look at the problem to see, is the x component of velocity in the positive x direction? Here it is. Is the y component in the positive y direction? Again, here it is. But if the ball had been at an elevation and had been thrown downward, then it's quite possible that one or both of these could have negative components. So you just have to be careful about the signs. All right, what else are we given? We are given, wow, that may be just about it, except there's one more piece of important information that we're not told in the problem statement, but it has to do with the highest point. Okay, so at the highest point, we should be able to figure out something about the velocity. Because at the highest point, we know if I draw in the vector that would indicate the velocity at that point, we know that the highest point means it's moving for just an instant horizontally. And v is the symbol we would use for that final speed. It's moving horizontally, so what do I know about the y component? The y component is 0, right? So that means v sub y at the top is equal to 0. What about vx? Well, vx is just v, right? So the speed at the top is just going to be the x component at the top. And we'll figure out what that is in just a minute. And this is really crucial. I've told you before that this is a piece of hidden information that you have to think about in order to realize. But upon a little bit of reflection, it's pretty clear that that has to be true. So with all that given information, what are we trying to find? We are trying to find, in part A, we're trying to find delta y. In part B, we're trying to find the speed at the maximum height, which is v. Right? Those are the two things. And those will be important in deciding which equation we should use. So let's go to the kinematic equations, and I will write them down again here. We know that vx equals vx0 because there's nothing more in that equation since the acceleration in the x direction is 0. That's all we've got. Then we could write that delta x is vx0t. Once again, that's all there is because there's no acceleration term. And those are really the only important kinematic equations for the x component of motion. In the y direction, we can say Vy is equal to Vy0 minus gt, because the acceleration in the y direction is negative g. And likewise, delta y is Vy0t minus a half gt squared. And there's one more equation I can write down for the y direction, Vy squared minus Vy0 squared equals negative 2g delta y. You might think, well, wait a minute, why didn't you write one of those down for the x direction? And if I do, I'll show you why I didn't do it. If I do, it would be Vx squared minus Vx0 squared equals, and on the right-hand side is the term involving the acceleration in that direction. But I know the acceleration in the x direction is 0, right? So that would just be 0. Well, that's kind of a simple equation. It's telling me that Vx is just equal to Vx0. And I knew that already because it was in the top equation. So this equation here doesn't really give us any additional information that we didn't already have. So here are the important equations, and now we have to think about what to do. We're still in the D, develop a plan stage. What are we going to try to do? Well, we're trying to find delta y. So we need an equation with delta y in it. We've got two possible equations here. This one, delta y, is in terms of time. And notice we have no information about time, how long it took for the ball to reach its maximum height. All right, since we have no information about that, we might think that we might want to use this last equation, because this last equation relates delta y to Vy, which we do know something about, right? We've just written that down, and Vy0, which we also know an expression for here. So that turns out to be the direct and simplest way of answering the question, is using this last equation with the squared terms and the velocity. I could, if I wanted to, use this equation, but it would involve t, and then I would have to do something to find t in this equation over here, or maybe in this equation up here, and combine them. That strategy might work. It might give me the right answer, but it would involve more work than just using this one directly. So the plan here is to use the Vy squared equation to solve for delta y. That's my plan. We'll see if it works. Right now, we move on to the evaluation stage. We're going to, just once again, this problem-solving strategy, the idea strategy, we start by identifying the problem, we develop a plan, and we evaluate the solution. So I'm writing this equation down right here. This is the equation, and I'll plug in the appropriate terms that we know. All right, so the left-hand side, Vy, we know that at the maximum height, that's 0. Vy0, okay, we've got, whoops, I need to say 0 minus Vy0 squared. Okay, so Vy0 up here is V0 sine theta, and that term has to be squared, equals negative 2g delta y. All right, I'm almost done, right? I'm going to solve for delta y. So with this equation, let me just realize that the minus signs on both sides cancel, right? So that this becomes V0 squared sine squared theta equals 2g delta y. And now to solve for delta y, I'm going to divide both sides by 2g, and that gives me the answer. Delta y equals V0 squared sine squared theta over 2g. That gives me the answer to part A. We'll come back and evaluate or assess this in just a minute once we solve part B. So now let's do part B. Part B was to solve for V at at the top. So what is v? V is the magnitude of the velocity vector at the top, and we already said that at the top the v is wholly horizontal, so it's just the x component. So whatever the x component of the velocity is initially stays the same all throughout. The x component of the ball's motion, the x component of the ball's velocity never changes. So I'll just write that down. Since Vx equals Vx0, and it never changes, right? Then at the top, v, which is what we want, is equal to Vx, which is equal to Vx0, and that's simply V0 cosine theta. And that's the answer. That's what we want for v. That's really simple, but let's just check one more time. Go back to the problem statement to see if we've satisfied what it says. It says your answer should be in terms of V0, theta, and g only. So let's take a look. For delta y, V0, theta, and g only. Right? There's a factor of 2, but that's okay. That's just a number. Over here, V0 and theta. No g in this equation, but it certainly satisfies the requirement that it only include those three. Right? It can't include a t or an a or anything else. So those are our two answers. Now the final step, and it's always important to do this, the assess step. Right? We don't have numbers provided, and so we can't really say, well, does the number make sense? But we can check units, and we can check signs. Okay? V as a speed should always be positive, and sure enough, this is a positive quantity as long as theta is an angle between 0 and 90. All right, so v is greater than 0, the sign checks out, right? And what about delta y? Delta y, if we look at this expression, it also is greater than 0 because we've got two squared terms in the numerator, and the denominator g is always 9.8, it's positive, so delta y is also positive, and that makes sense too, going back to the sketch for just a minute. Right? It's clear that y final at the top is higher than y initial, which was at the origin. So delta y, final minus initial, should be positive, no doubt. So those two are good. And now we can check units. Okay, so we've checked signs, now we'll check units. It's easy enough to do this for v, right? Because the bracket around v means the units of v. The units of v are going to be, according to this equation, the units of another velocity. Cosine theta, that doesn't have any units, and so it makes sense that the units of velocity are the same as the units of what's on the right-hand side, which is also velocity. That was an easy check. This one over here for delta y, let's check that out. The units for delta y should be a distance, but let's check. So they're going to be the units of a velocity squared, right? Sine theta doesn't have any units, divided by the units of g, right? So this is the numerator. A square of a velocity will be meters squared per second squared. The denominator is meters per second squared, and I can see that the second squared terms cancel out, and I'm left with meters squared over meters, which is just meters, right? So this tells me that delta y is going to end up with units of meters according to my answer, and that's as it should be. That checks out too. So the problem is finished. If we had numbers for the initial velocity and for the angle, we could calculate numerical values, but they weren't given to us, and that's okay. We followed all the steps. We followed the I, identify the problem. D, draw a sketch and develop a plan. E, evaluate in order to solve for the quantities that we're trying to find. And finally, A, to assess the answers that we get and see if they make sense. And here we did that, right, with signs and with units. Please, as you work on these problems, you're working on these in the notebook. Even the problems that you're submitting online, you should be solving in a notebook. Make sure you work through these steps. And the more practice you get, the easier it will get to solve these problems. And we will continue to work on this in class and as you work on the homework. So, I will see you in class.